The barren dust of Mars could one day bloom, transformed by trillions of silent, microscopic engineers. This is the promise of biological engineering for space, a field turning science fiction into tangible reality. We are entering an era where the smallest life forms on Earth hold the blueprint for building sustainable worlds far beyond our own. By the end of this exploration, you will understand how scientists are reprogramming microbes to become planetary construction crews, life support systems, and factories, fundamentally changing our future among the stars. How will we prevent these engineered organisms from overwhelming an alien world? And can we truly manage an ecosystem on a planetary scale? This journey reveals a future where we cultivate the cosmos instead of merely conquering it. What does it mean to become a gardener of entire worlds? Mars Reborn is a world of deep green valleys and vast blue lakes, sheltered under a sky we could one day breathe. This dream of terraforming has captivated storytellers for generations, a future where we remold entire planets in Earth's image. Yet the classic path to this future was one of almost unimaginable scale, demanding technology on a level that could reshape a world. Enormous mirrors in space, larger than cities, would focus sunlight to melt polar ice. Factories covering the landscape would churn out breathable air for centuries. It was a vision of raw power, a human versus planet struggle requiring immense energy and time. But a new, far more subtle strategy is emerging from the laboratories of today. Instead of fighting a world's environment, we could recruit nature's own smallest engineers to cultivate it for us. This biological path uses specially designed microbes to perform the same epic tasks, but slowly, gently, and sustainably. Imagine organisms that consume the thin Martian carbon dioxide and release oxygen as a natural byproduct. Others could pull essential nitrogen from the atmosphere and lock it into the barren soil, creating the foundation for agriculture. They might even help regulate the very pressure of the air, making it thicker and warmer over time. This approach does not invent a new process from scratch. It borrows from a toolkit refined over billions of years of evolution on our own planet. We are learning to redirect that ancient, proven ingenuity toward a new purpose. The shift is profound, moving from colossal industrial force to the elegant choreography of life itself. This changes our entire relationship with space, setting the stage for the tiny but mighty organisms poised to make this grand vision a reality. Our own planet holds the blueprint for this transformation, a story written in the earliest chapters of life on Earth. Long before plants or animals existed, a humble microbe called Cyanobacteria began a planetary renovation project that would ultimately make our world breathable. These ancient organisms were the original terraformers, using sunlight to split water molecules and releasing oxygen as a waste product over billions of years. They are the ultimate pioneers, thriving in some of the most punishing environments on our planet, from scorching deserts to frozen Antarctic valleys. This inherent toughness makes them a perfect candidate for the harsh conditions of another world. Scientists are now working to enhance their natural resilience, creating super strains designed to withstand intense space radiation, the near vacuum of low pressure, and the toxic chemistry of Martian soil. Imagine deploying these engineered cyanobacteria across the Red Plains. They would get to work using the abundant carbon dioxide in the thin atmosphere, converting it through photosynthesis into both oxygen and organic compounds. This process would slowly, steadily begin building the foundation of a new atmosphere, but their talents do not end with air. Cyanobacteria naturally form dense, living mats that bind loose soil together, preventing destructive dust storms and creating a stable surface. These mats become the very first layers of a new, living crust, a precursor to soil where other organisms could one day take root. By harnessing these primordial engineers, we are not inventing a new technology from scratch. We are replaying Earth's greatest biological success story on a new stage, a proven method for turning a barren rock into a living world. Of course, for any life to truly flourish, it needs more than just air and stable ground. It needs the fundamental building blocks of biology, the very nutrients that fuel growth. Deep within the Martian crust, in pitch-black lava tubes where temperatures plunge far below freezing, another kind of microbial architect is already at home. These are the extremophiles, nature's ultimate survivors that flourish in places that would be instantly fatal to almost any other form of life. On Earth, we find them thriving in boiling acid pools, in the crushing pressures of the deep ocean, and in rocks saturated with radiation. Their very existence redefines the boundaries of the habitable, and for space settlement, they are a gift of unimaginable value. Scientists are now learning to direct their unique talents. Consider the Chemolithotrophs, a name that simply means they eat rocks. These incredible organisms derive all their energy from inorganic chemicals within the stone itself, breaking down minerals and releasing useful compounds as a byproduct. On a world like Mars, engineered versions of these microbes could be released into the subsurface, where they would tirelessly process the local rock, slowly extracting water trapped in minerals, releasing breathable oxygen, and even leaching out valuable metals like iron and magnesium for future construction. Their natural resilience to radiation and extreme temperature swings makes them perfect pioneers not just for Mars, but for the icy, ocean-bearing moons of the outer solar system. On Europa or Enceladus, where a frozen shell hides vast subsurface seas, these microbes could be the first to establish a foothold in the darkness, creating a chemical foundation for more complex ecosystems to follow. By studying and modifying these ultimate survivors, we are not just building tools, we are learning the fundamental rules of life in the cosmos. This knowledge is the key to moving beyond simply planting flags and leaving footprints, toward creating habitats that can truly sustain themselves, generation after generation. This ancient cycle of renewal is the same principle that will sustain us on our longest journeys. Within the confined walls of a spacecraft or a lunar habitat, every single resource becomes precious, and the idea of waste is a luxury we cannot afford. This is where the concept of a bioregenerative life support system comes into play, a closed-loop environment that functions much like a miniature, self-sustaining forest. In a thriving forest, nothing is truly discarded. Fallen leaves decompose to nourish the soil, which in turn feeds the trees that produce the oxygen animals breathe. We can engineer this same elegant balance for a starship. The key to making this work lies with our microscopic allies, engineered microbes that act as the ultimate recyclers. Imagine a system where the water an astronaut uses is not discarded but purified by a community of specialized bacteria, breaking down any impurities and returning it clean to the habitat supply. The very air we exhale, rich in carbon dioxide, becomes a feedstock for chambers of algae. These algae, powered by light, consume the carbon dioxide and regenerate a fresh supply of breathable oxygen. Even the most challenging forms of organic waste can be transformed. Certain bacteria possess the incredible ability to break down complex molecules, the kind found in human waste, into simpler, usable compounds like nitrates and phosphates. These nutrients then become fertilizer, feeding plants grown for food within the habitat. This creates a beautiful, symbiotic cycle where what was once considered refuse becomes the literal fuel for life and growth. This biological approach is a game changer for deep space exploration. By closing the loop, we drastically cut our dependence on endless resupply missions from Earth, making long-term settlements on the Moon or Mars not just a scientific dream, but a logistical and economic reality. These microscopic recyclers do more than just clean up. They create the foundation for a permanent human presence, and as we will see, they can also become the very source of our nourishment. The ultimate test of a closed-loop system is its ability to create something new from almost nothing, turning the basic chemistry of an alien world into the very stuff of life. Inside a future Martian habitat, the most vital room might not be a pantry stocked with Earth-bound supplies, but a softly humming bioreactor. Within its warm, nutrient-rich broth, trillions of engineered yeast cells are hard at work. These are not the yeasts that make bread rise, but microscopic factories, reprogrammed through synthetic biology to perform a new kind of alchemy. Scientists design them by inserting carefully selected genetic instructions, creating custom metabolic pathways that tell the cell how to transform raw, local ingredients into something priceless. The inputs are simple and abundant: carbon dioxide siphoned from the Martian atmosphere and hydrogen extracted from water ice. The output, however, is a nutrient-dense paste of fats and proteins, a foundational food source produced on demand, right where it is needed. This biological manufacturing principle extends far beyond basic nutrition. The same type of microbial factory could be tuned to produce bioplastics, feeding a three-dimensional printer that fabricates replacement parts or tools without a single item shipped from Earth. In a medical bay, another specialized strain could synthesize complex pharmaceuticals like antibiotics or vital medications, starting from simple precursor molecules found in the local environment. This transforms the immense challenge of interstellar supply chains from a logistical nightmare into an elegant, manageable biological process. It represents a profound shift toward true resource independence, where survival is not about what you bring with you, but what you can build with what you find. This self-sufficiency hinges entirely on our ability to work with a world, not against it, tapping directly into the raw materials that already exist there. The ground beneath our feet on another world is more than just dust. It is a treasure trove of raw materials. Accessing those materials, however, presents one of the greatest challenges of space settlement. Traditional mining, with its massive machinery and destructive environmental impact, is simply not feasible on a fragile, alien landscape. The energy required would be staggering, and the process would generate immense amounts of waste, a burden we cannot afford in a closed environment. But there is a quieter, more elegant way, a process refined by nature over billions of years. It is called bioleaching, and it uses the natural chemistry of microbes to extract precious metals directly from rock. Imagine a simple vat filled with crushed lunar soil and water. Into this mixture, we introduce a specialized bacterium like Shionella oneidensis. This remarkable microbe does not need to chew or dig. Instead, it performs a kind of microscopic alchemy, using its own metabolism to alter the electrical charge of metal ions. This change makes the metals, things like iron, magnesium, and aluminum, dissolve right out of the crushed rock and into the water where they can be easily collected. This is biological mining. The process is incredibly precise. By selecting different strains of bacteria or tuning their environment, we can target specific elements crucial for our survival and construction. We could program these microbial miners to extract iron for building structures, magnesium for alloys, or even rare earth elements for electronics. all of this happens at room temperature with minimal energy input beyond what the bacteria themselves need to live. The profound implication is that we no longer need to launch every gram of metal from Earth at an astronomical cost. We can literally grow our infrastructure from the ground up, turning the very substance of an alien world into the bones of a new civilization. This is the ultimate form of in situ resource utilization, and it reshapes our entire approach to living in space, moving from being temporary visitors to becoming true inhabitants who build with the materials at hand. The materials for our future homes will not be quarried or smelted, but cultivated. Imagine walking through a structure on the moon where the walls themselves are alive, grown from a dense, interwoven network of fungal mycelium. This is not a distant fantasy, but a tangible vision of biofabrication, where we guide biology to build for us. Mycelium, the root-like structure of fungi, possesses an incredible natural talent for creating strong, resilient matrices. By combining these fungal networks with Lunar or Martian Regolith, we can produce composite materials that are both remarkably lightweight and incredibly strong. The process is elegantly simple. We provide the mycelium with a nutrient source and a mold in the shape of a brick or a structural panel. The living organism then grows, filling the form completely and binding the regolith dust into a solid, cohesive whole. Once the growth is complete, the material is gently heated to stop the biological process, leaving behind a durable, fire-resistant building block. Perhaps most astonishing is its inherent ability to self-heal. If a crack forms, reintroducing nutrients and the right conditions can encourage the mycelium to regrow, seamlessly repairing the damage. This is construction that maintains itself. In parallel, another biological builder is at work. A common soil bacterium known as Sporosarcina pasteuriae offers a different kind of alchemy. When mixed with local sand and a nutrient solution, these microbes initiate a natural chemical process. They precipitate calcium carbonate, the primary component of limestone, effectively gluing the sand particles together into a solid, rock-like material. This bacterial concrete can be poured into any shape, hardening into sturdy structures without the immense energy cost of traditional cement production. Together, these biological methods represent a fundamental shift in how we create our surroundings in space. We are moving away from the sterile, imported metal cans of early exploration and toward habitats that are literally grown from the ground up. These structures are not just placed on the landscape, they become an integrated part of it, the first step in transforming a sterile terrain into a truly living world. But to sustain a living world, we must first master the art of cultivating its most vital resource, food, in the most unlikely of places. The soil of Mars is a sterile, powdery dust, chemically hostile and utterly lifeless. It contains no decaying leaves, no broken-down roots, and none of the rich organic matter we call humus that gives Earth's soil its fertility and its remarkable ability to hold onto water. This regolith is not just empty, it is actively repellent to life as we know it, laced with perchlorate compounds that are toxic to most plants. To transform this barren ground into a foundation for gardens and forests, we must first create soil from scratch, a process that on Earth took nature millions of years, but that we can now jumpstart with a carefully selected microbial workforce. The first members of this team are the decomposers, a consortium of bacteria and fungi whose natural role is to be nature's ultimate recyclers. Within a future habitat, all organic waste, from food scraps to inedible plant matter, would be fed to these microbes. They diligently break down this complex material, converting it into stable, nutrient-rich humus. This dark, earthy substance is the magic ingredient. it begins to bind the loose, toxic dust into aggregates, creating structure, and for the first time, giving the Martian ground the capacity to retain precious water instead of letting it instantly evaporate or drain away. At the very same time, another group of microbial specialists gets to work on the atmosphere. Nitrogen is essential for all life, forming the backbone of proteins and DNA. Yet the nitrogen gas that makes up a portion of the Martian air is utterly inert, useless to plants in that form. This is where nitrogen-fixing bacteria, like various strains of rhizobia, perform their quiet miracle. They possess a unique enzyme that can crack the powerful triple bond holding nitrogen molecules together, combining the freed nitrogen atoms with hydrogen to form ammonia, a soluble compound that plants can readily absorb and use for growth. This partnership between decomposers building soil structure and nitrogen fixers enriching it creates the initial conditions for pedogenesis, the formal term for soil formation. It is a slow, deliberate act of world building, one microbe at a time, laying down the literal groundwork for future agricultural plots and one day complex ecosystems. Yet this entire biological symphony depends on a single, flowing conductor, the element that enables every chemical reaction and sustains every living cell: water. The sterile ground of Mars holds its water locked away not in flowing rivers, but in deep frozen deposits buried beneath the surface. Accessing this vital resource has always posed a monumental engineering challenge, one that typically demands heavy machinery, immense energy, and complex purification plants. But a far more elegant solution is emerging, one that uses living technology to gently coax water from the ice. Picture a vast, dark, gelatinous sheet spread across a frigid plain. This is no simple blanket, it is an engineered microbial mat, a cooperative community of trillions of organisms working in unison. The top layer is rich in dark pigmented cyanobacteria, designed to act as a biological solar panel. They absorb the weak Martian sunlight and convert it into heat, warming the ground beneath them just enough to initiate a slow, controlled thaw. As the subsurface ice begins to melt, the water is drawn upward into the mat's dense, fibrous biofilm. This living matrix is the heart of the system. It functions as a multi-stage, self-cleaning filter. The sticky extracellular substances secreted by the microbes trap fine dust and particulate matter. More importantly, specialized bacterial strains within the mat possess metabolic pathways that allow them to actively break down toxic compounds like perchlorates, transforming them into harmless chloride and oxygen. Simultaneously, other engineered cyanobacteria act as microscopic sponges, sequestering heavy metals from the water and storing them safely within their own cell structures. The result is a passive, continuous trickle of purified water, collected at the base of the mat, ready for use. This is not a machine that can break down. It is a living system that sustains and even repairs itself as long as the sun shines. By creating these biological water harvesters, we secure the most essential ingredient for all future efforts, from drinking water for astronauts to the nutrient solutions that feed our soil-building microbes and our closed-loop life support. With a reliable water cycle now in place, our attention turns upward to the thin, unbreathable veil of the sky itself. The thin Martian air is a silent ocean of carbon dioxide, a global blanket that cannot sustain human life yet holds the key to creating one that can. Transforming this vast reservoir into a breathable atmosphere is a task of almost geological patience, but we possess a tool that works on exactly that timescale: life itself. The same engineered cyanobacteria we met as soil pioneers can be scaled up to become planetary lungs. Imagine releasing trillions of these microscopic organisms, not just onto the ground, but suspended within the atmosphere itself. Encased in protective, transparent membranes, they would float like a faint, living haze, each cell a tiny factory using sunlight to split the abundant carbon dioxide. Their waste product, the oxygen we need to breathe, would be released slowly and steadily, molecule by molecule, beginning the multi-century process of thickening the air and shifting its very chemistry. This is the concept of a biological pump, a self-replicating workforce that uses the exponential power of reproduction to achieve what no machine ever could. As each microbe divides, the workforce doubles, accelerating the transformation over generations. We could guide this process by deploying them in vast, managed bioreactor farms on the surface, sprawling facilities that look less like industrial plants and more like shallow, sun-drenched lagoons, carefully controlling their growth and oxygen output. This is not a quick fix, it is a legacy project, a commitment to a future we may not live to see but can set in motion today. It requires us to think like gardeners of an entire world, nurturing a planetary-scale ecosystem from its first fragile breaths. To succeed, we must learn to conduct this microscopic orchestra, understanding how these trillions of individual lives interact to shape a global environment. This grand vision of planetary gardening rests on a foundation of profound responsibility. We are discussing the release of self-replicating, engineered life into an alien environment, an act with consequences that could echo for millennia. What happens if a microbe designed for extreme resilience escapes a controlled habitat and begins to thrive unchecked in the pristine Martian wilderness? The very traits that make these organisms perfect pioneers, their toughness and ability to multiply, also represent a significant ecological risk. An uncontrolled proliferation could irrevocably alter the very world we seek to understand and settle, potentially overwhelming any native Martian life forms we have yet to discover. To prevent this, scientists are developing sophisticated biocontainment strategies that are built directly into the organism's genetic code. One approach involves engineering what are often called suicide genes. These are genetic switches programmed to activate if the microbe leaves its designated area. For instance, a bacterium used inside a water purification tank could be designed to rely on a specific, laboratory-made nutrient that simply does not exist in the natural Martian environment. The moment it escapes and loses access to that vital compound, its self-destruct sequence would engage, safely terminating the cell. Other designs might tie the organism's survival to a narrow band of temperature or atmospheric pressure that only exists within our enclosed habitats. This is not about creating fragile life, but about building inherent safety switches into powerful biological tools. The development of such protocols is as much an ethical endeavor as a technical one. It forces us to confront our role as stewards, not just conquerors of new worlds. This has sparked urgent conversations among scientists and policymakers about establishing strict international guidelines for biological engineering in space. The goal is a universal framework that prioritizes planetary protection, ensuring that our efforts to cultivate one world do not inadvertently destroy another's unique scientific heritage or future potential. The stakes extend far beyond a single mission, touching on the integrity of entire ecosystems we are only beginning to imagine. This leads us to a deeper question about the legacy we wish to create among the stars, a future built not on dominance, but on a harmonious and carefully managed coexistence. These ethical questions reach far beyond containment, touching on the very purpose of our journey. At the heart of the debate lies the profound concept of directed panspermia, the intentional seeding of life from one world to another. One perspective frames humanity as a steward of life's flame, carrying its spark to the cosmic darkness. In this view, our highest calling is to cultivate barren worlds, transforming silent deserts into thriving biomass as part of life's grand cosmic expansion. The opposing philosophy holds that other worlds are priceless natural laboratories, their pristine states sacred for scientific discovery. From this vantage point, introducing earthly microbes, even engineered ones, would be an irreversible act of contamination, forever destroying our chance to understand a unique chapter in the story of the universe. This is not merely a technical disagreement, it is a deep philosophical divide over whether our role is that of a gardener or a guest. International policy has long grappled with this tension. For decades, the Committee on Space Research, known as COSPAR, has maintained planetary protection protocols. These are essentially planetary quarantine rules designed to prevent biological contamination from Earth from compromising the search for alien life. Their guidelines are strict, especially for missions to places like Mars or Europa where life might exist. But these policies were written for an era of robotic explorers, sterile probes designed to look but not touch. They are not equipped to handle the new reality of biological engineering, where living, self-replicating systems are the primary tools for settlement. The old model was about preventing contamination. The new challenge is about managing an ecosystem we intentionally introduce. This demands a complete evolution of the rules, moving from a simple prohibition to a complex framework for responsible cultivation. We would need to define planetary parks, zones of absolute preservation, while designating other areas as development zones where biological engineering is permitted under rigorous oversight. The path we choose will ultimately define humanity's legacy. Will we be remembered as the generation that brought a silent world to life, or as the one that carelessly erased its unique scientific heritage before it could be understood? The answers we forge here on Earth will directly shape our next most critical step. After proving these technologies in the safety of our laboratories, we must test them in the unforgiving environment of space itself. High above the Earth, a silent laboratory orbits through the void, its modules bathed in the alternating glare of the sun and the deep cold of shadow. The International Space Station serves as our most critical bridge between the controlled safety of Earthbound labs and the untamed wilderness of deep space. Within its specialized experiment racks, Petri dishes hold communities of engineered microbes, living through conditions we can only simulate imperfectly on the ground. Here, in the persistent microgravity and the intensified stream of cosmic radiation, we witness evolution in fast forward. Scientists monitor these cultures not just for survival, but for change, observing which genetic adaptations emerge when life is pushed to its limits far from home. This real-time feedback is irreplaceable, revealing how a bacterium's metabolism might shift without gravity to guide its movements, or how its DNA repairs itself under a constant particle barrage. One recent investigation cultivated protein-rich fungi, not in a nutrient broth, but directly on a substrate designed to mimic the harsh, barren chemistry of Martian soil. The success of this endeavor is about more than just growth. It is a test of an entire biological chain. Can these organisms find and process the scant traces of useful minerals? Will they produce the expected nutritional output when stressed by off-world conditions? The answers, growing in those silent culture dishes, directly shape the design of future life support systems. In another part of the station, a compact, closed-loop system tests the resilience of microbial water recyclers. Tiny communities of bacteria are tasked with purifying a simulated wastewater stream, showing us if their cleaning efficiency holds up when they cannot rely on Earth normal convection currents or fluid dynamics. A failure here, in the gentle cradle of low Earth orbit, saves us from a catastrophic failure years later on a Martian outpost, where every drop of water is a treasure. The data flowing down from these orbital experiments is the key to de-risking humanity's greatest leap since Apollo. It transforms theoretical biological tools into validated, flight-proven technology. Each small validation builds confidence, turning a grand vision of cosmic gardening into a series of manageable, incremental steps. These painstaking trials in our orbital outpost are preparing us for the next logical phase, a destination close enough for rapid response yet alien enough to be the ultimate test. Our next stop is a world of dust and silence where the lessons from the station will be put to work under a black sky. Floating in the void between Earth and the Moon, the Lunar Gateway represents a profound shift from outpost to workshop. This is not merely a way station for astronauts, but a dedicated biological foundry, a place where our microscopic allies face their most rigorous exam yet. Within its specialized modules, far beyond the comforting shield of Earth's magnetosphere, advanced bioreactors and environmental chambers will hum with activity. Here, the microbial systems we rely on for air, water, and food will endure the true, unfiltered conditions of deep space. The radiation is more intense, the isolation more complete than anything simulated on the International Space Station. This is the necessary crucible, a test of resilience that cannot be fully replicated on Earth. Can a community of water-purifying bacteria maintain its delicate balance for months or even years without human intervention? Will a batch of protein-producing yeast consistently deliver the same nutritional output when bathed in a constant stream of cosmic rays? The gateway provides the platform to find out, allowing us to observe these biological systems over long durations and under relentless stress. Success in this harsh classroom is the only path to trusting these living technologies with human lives on the multi-year journey to Mars. A failure in cislunar space is a data point, a lesson learned, but a failure on a Mars transit could be catastrophic. By proving that these biological loops can run reliably and autonomously, the gateway becomes the essential bridge, transforming terrestrial theory into hardened extraterrestrial fact. This philosophy of testing and validation in the most realistic environment possible will extend all the way down to the architecture of the Martian surface itself. The first true Martian city will breathe. Its architecture is not one of cold metal and sterile corridors, but a living tapestry woven from biology itself. Picture a central hub not of a power plant, but of a digestive system. Here, vast, warm bioreactor farms pulse with trillions of engineered microbes, transforming carbon dioxide and local minerals into a steady stream of nutrient paste for the inhabitants and raw bioplastics for the three-dimensional printers that fabricate tools. The air carries a faint, earthy scent, not of machinery but of life. Radiating from this core are the living quarters, their walls grown from a dense matrix of fungal mycelium interwoven with Martian regolith. These are not inert structures, they are active, breathing surfaces. If a meteoroid puncture scars a wall, a nutrient solution is applied, and the embedded mycelium slowly knits the wound closed, a self-healing process that requires no external parts or complex repairs. Above it all, vast geodesic domes arch toward the pink sky, their transparent panels shielding the most ambitious project of all. Inside these domes, the first patches of genuine Martian soil are being cultivated. Engineered decomposer microbes break down organic waste from the habitat into rich humus, while nitrogen-fixing bacteria work in concert with the roots of hardy pioneer plants to slowly, patiently build a true, arable Earth. This entire settlement operates on a principle of elegant redundancy. The carbon dioxide you exhale is a crop for the algae in the life support system, which gives you back oxygen. The water you use is purified by bacterial communities and returned to you clean. Your organic waste becomes the fertilizer that feeds the plants that become your next meal. Every output is an input in a different loop. The city functions as a superorganism with its microbial workforce acting as a collective metabolism, a circulatory system for resources, and a respiratory system for the very air. This holistic design is not just for efficiency, it is the key to permanence. By weaving biology into the very fabric of the city, we move from being fragile visitors in a hostile environment to becoming a resilient, integrated part of a new world, a society that truly lives with the land, not just on it. Orchestrating a planetary ecosystem is a symphony with trillions of musicians, a composition far too complex for any human conductor to lead alone. This grand undertaking demands a partner, an intelligent system capable of sensing, analyzing, and responding to the environment on a global scale. The solution lies in a planetary biocontrol network, a seamless fusion of artificial intelligence and autonomous robotics designed to manage our microscopic workforce. Picture a swarm of small, solar-powered robots like diligent gardeners fanning out across the Martian landscape. They do not build or dig, instead, their purpose is to observe. Each robot is equipped with sophisticated sensors, constantly tasting the air to measure shifts in oxygen and methane, probing the soil to check the density and health of microbial mats, and monitoring the regolith for signs of unintended biological spread. This constant, real-time data flows back to a central artificial intelligence, a digital mind tasked with viewing the entire planet as a single, interconnected biological machine. The AI's role is predictive. It runs countless simulations, modeling the potential outcomes of a sudden temperature drop in the northern plains or the effect of a new nutrient release in the southern highlands. It can foresee a microbial community beginning to struggle or, conversely, growing too aggressively in an unplanned direction. When such an imbalance is detected, the AI can dispatch its robotic agents to deliver a precise intervention. A drone might release a targeted aerosol of nutrients to bolster a faltering colony of cyanobacteria. Another robot could deposit a slow-release containment agent around a protected scientific zone, creating a chemical barrier to ensure our engineered life respects its designated boundaries. This is not about control in a rigid sense, but about guidance, about nurturing a living system toward a stable, resilient future. The true power is in the synergy, the partnership between the creative, adaptive intelligence of biology and the vast, analytical capacity of machine learning. This collaboration between the born and the built is the only way we can hope to cultivate an entire world, ensuring that the future we are building among the stars is both thriving and secure. The staggering economics of spaceflight make this biological shift not just elegant but essential. Every single kilogram of payload launched from Earth to Mars carries a price tag that can soar into the hundreds of thousands of dollars. This is the fundamental bottleneck for any dream of a permanent settlement. We cannot afford to ship everything we need for generations, from building materials to fertilizer. But what if, instead of launching tons of machinery, we sent a single, carefully packed kilogram of microscopic spores? These engineered seeds would weigh almost nothing, yet upon arrival, they would awaken and get to work. They would multiply exponentially, using the sunlight, atmospheric gases, and soil minerals already present on Mars to produce oxygen, purify water, and manufacture bioplastics. The initial capital investment plummets, transforming a multi-trillion-dollar logistical nightmare into a manageable, scalable business plan. This is the core of the economic argument for biological engineering. It replaces the immense cost of constant resupply with the elegant, self-replicating power of life itself. The business case extends far beyond simple cost savings into the realm of entirely new revenue streams. Imagine a future where the most valuable miners in the solar system are not humans in pressurized suits, but trillions of microbes working inside automated asteroids. Certain engineered bacteria are exceptionally good at bioleaching, the process of extracting precious metals from rock. An asteroid rich in platinum group metals could be processed not with massive, fuel-guzzling machinery, but with a carefully introduced microbial culture. These organisms would quietly and efficiently dissolve the valuable metals out of the ore, creating a concentrate that could be harvested at a fraction of the energy and equipment cost of traditional methods. This could finally make asteroid mining a profitable venture, opening up resources worth quadrillions of dollars without the environmental impact of terrestrial mining. Back in orbit, another industry emerges. The unique conditions of microgravity can enable microbes to produce substances impossible to create on Earth, from perfectly spherical pharmaceutical compounds to novel, ultra-strong protein crystals. A specialized yeast strain cultured in a space station bioreactor could synthesize a rare, life-saving drug with unprecedented purity, a product that could only be made off-world. These space-manufactured goods would command a premium, creating a high-value export market that flows back to Earth. This economic potential is the crucial catalyst. While government agencies can fund the initial research, it is the influx of private capital from companies seeking these new markets that will truly accelerate our future among the stars. The vision of a living, breathing Martian city shifts from a far-off dream to a sound investment, one built not on brute force but on biological ingenuity. This financial logic inevitably pushes our ambitions further, beyond the red dust of Mars to the true final frontier. This cultural transformation hinges on a simple truth we often overlook. We have been biological engineers for thousands of years. The ancestor of every ear of corn you have ever eaten was a nearly inedible wild grass. The friendly dog by your side shares a lineage with the ancient wolf. This is selective breeding, a slow, patient form of genetic redirection that has shaped the very world around us. Modern techniques like genetic modification are not a radical break from this past. They are simply a more precise and efficient set of tools for the same fundamental purpose, guiding life to meet human needs. The difference lies in the timescale and our direct intent, moving from unconscious selection to conscious design. This reframing is essential for overcoming the instinctive unease that accompanies the idea of engineered life. The phrase "playing God" carries a heavy cultural weight, yet it is a charge that could have been leveled at the first farmers who saved the best seeds for the next planting. Our responsibility is not to avoid this power, but to wield it with profound wisdom and foresight. Building public trust will require radical transparency, opening the doors of laboratories and sharing both the immense potential and the carefully managed risks. We must move the conversation beyond the sterile language of laboratories and into the language of human aspiration. This is where storytellers become our most vital partners. Artists can paint the vision of a child tending a garden under a Martian dome. Filmmakers can craft narratives where the heroes are not soldiers, but biologists and ecologists working to birth a new world. These stories can transform public perception from a fear of contamination to a hope for creation. They can replace the chilling image of an invasive species with the inspiring vision of a cultivated ecosystem, a place where humanity acts as a careful steward nurturing life into being. This cultural shift is not a secondary concern. It is the bedrock upon which our entire future in space depends. A society that fears the tools of biological engineering will never authorize their use. But a society that sees them as instruments of cultivation, as the means to build a home among the stars, will provide the sustained support and visionary drive needed for this multi-generational project. The final frontier is not a void to be crossed, but a garden to be planted, and we must all learn to see ourselves as its gardeners. The universities training these future pioneers will not look like the campuses of the past. Their laboratories will be hybrid spaces where students in white coats manipulate DNA sequences on screens right beside glove boxes filled with simulated Martian regolith. They are not just learning biology or engineering in isolation. They are mastering the new hybrid discipline of astromicrobiology, which studies how life adapts and functions in off-world environments, and space synthetic biology, which focuses on redesigning organisms for specific extraterrestrial tasks. This is a curriculum built on interconnection. A single project might require a student to understand the metabolic pathways of a nitrogen-fixing bacterium, the geological composition of lunar soil, the engineering principles of a closed-loop bioreactor, and the ethical frameworks for planetary protection. The goal is to produce a new kind of professional, one who sees a future Martian habitat not as a machine to be maintained, but as a living, breathing ecosystem to be tended. These bioastronauts will be as comfortable taking a soil sample to check microbial health as they are piloting a rover. They will diagnose a problem in the water recyclers by analyzing the bacterial community balance, not just by checking a pressure gauge. Their most vital skill will be a form of cosmic empathy, the ability to think from the perspective of the biological systems they manage, anticipating needs and stresses in a web of life that has never existed before. This educational shift is already beginning, with specialized programs and research institutes emerging at the intersection of space science and biology. Investing in these minds is the most critical mission preparation of all. The success of our grandest cosmic ambitions ultimately depends on the cultivators, the guardians who will learn the language of these new worlds and gently guide life to take root among the stars. This search for native life is our first and most profound responsibility. Before we introduce our own engineered organisms, we must listen for a heartbeat that is not our own, a biological signature that evolved separately from everything on Earth. The most promising places to listen are the buried oceans of icy moons like Europa and Enceladus. Far beneath their frozen crusts, in perpetual darkness, vast saltwater seas may hold ecosystems built not on sunlight but on chemical energy. On Mars, the search focuses on the deep subsurface, where layers of rock might offer protection from radiation and preserve traces of ancient microbial communities, or perhaps even sustain them still. Discovering any form of life, however simple, would be a transformative event for our species. It would answer the ancient question of whether we are alone, proving that life is not a singular miracle on Earth but a natural, recurring phenomenon in the cosmos. Beyond its philosophical impact, such a discovery would offer a masterclass in alien biology. We could analyze its fundamental architecture. Is its genetic code written in DNA or in something entirely different? Does it use the same amino acids as life on Earth, or has it found a different path? Every detail of its biochemistry would be a blueprint for survival in an environment we find utterly hostile. This knowledge would revolutionize our own biological engineering efforts. An organism that thrives in the sub-zero, high-pressure darkness of a European ocean might possess enzymes that function perfectly in the cold, ideal for running industrial processes in the shadowed craters of the Moon. Its method of extracting energy from rock and water, a process called chemosynthesis, could inspire far more efficient ways for our own microbes to produce food and fuel on other worlds. We are not just looking for life, we are looking for a new biological language, one that could teach us how to live in the universe on its own terms. This quest for discovery and the project of engineering are two sides of the same mission, a continuous dialogue between learning what is and designing what could be. The leap from a single world to a galactic civilization begins with a choice to build with the universe instead of fighting against it. Centuries from now, the definition of a habitable world will have expanded beyond the narrow Goldilocks zone. An icy moon orbiting a gas giant, a barren rock drifting in the void, even a large asteroid could become a home pre-conditioned by a silent, patient workforce. Engineered microbes would serve as our advanced scouts, launched by the billions on autonomous arc ships. Upon arrival at a target body, these pioneer species would awaken and begin their foundational work, a process spanning generations. They would extract water locked in minerals, slowly building subsurface aquifers. They would process the local rock, releasing gases to form a thin, initial atmosphere and breaking down the regolith into the first crude soil. This is not terraforming in the classic sense. It is a form of cosmic acclimatization, preparing the ground long before the first human footstep. The very infrastructure of a settlement would be grown in place. Bacterial concrete would form landing pads and radiation shields, while fungal mycelium would weave itself into the structural bones of habitats, using the local dust as its building material. These microbial networks create the physical and chemical scaffolding upon which everything else depends. Only after this biological groundwork is firmly laid would more complex ecosystems be introduced, starting with hardy lichens and mosses, building step by step toward a functioning biosphere that can support human life. This approach fundamentally rewrites the economics and ethics of expansion. We are no longer limited to the handful of planets that resemble Earth. Instead, we can cultivate millions of potential homes, transforming the galaxy from a collection of hostile outposts into a connected, living network. This grand vision of a biologically enabled future is not a sudden leap, but a path we are already walking. Every experiment on the International Space Station, every new strain of bacteria engineered to withstand radiation or produce nutrients, is a step toward that incredible reality. The work in today's laboratories is the quiet, determined beginning of a journey that will ultimately see life and intelligence flourish across the cosmos. This breathtaking potential is shadowed by a profound responsibility, for the very power of life to adapt and multiply is also its greatest risk. An engineered microbe designed for a single purpose is not a static machine. Its genetic code can change over generations, a natural process of mutation accelerated by the intense radiation of space. A bacterium programmed to extract iron might, through a series of small changes, lose that ability entirely, leaving a mining operation stranded. In a far more concerning scenario, a random mutation could alter its metabolism, causing it to secrete a compound harmful to other life, effectively becoming a pathogen within the closed environment of a habitat. This is not a prediction of doom, but a fundamental law of biology we must design around. Our solutions must be as dynamic and resilient as the life forms we aim to guide. The scale of planetary engineering introduces another layer of complexity, where local fixes can have global consequences. Releasing dark, heat-absorbing microbial mats to melt ice could inadvertently alter regional atmospheric pressure, triggering unpredictable dust storms that shroud the planet. A process intended to warm the planet might release subsurface reservoirs of carbon dioxide too quickly, creating a runaway greenhouse effect that makes the world less habitable, not more. We are learning to think in systems, not just in singular solutions, understanding that a planet is a complex web of feedback loops we are only beginning to map. The most irreversible risk lies in the act of contamination. The moment we introduce any Earth-born organism to another world, we forever change its biological destiny. A hardy, engineered microbe could outcompete and obliterate a fragile, native Martian organism we never even detected, erasing a unique chapter in the story of life before we could read its first page. This would be a scientific loss of cosmic proportions. These possibilities are not arguments for inaction, but the very reason we must proceed with meticulous care. They demand a new paradigm of safety built on redundant biological containment, painstaking incremental testing in isolated orbital labs, and unwavering international cooperation. The goal is not to eliminate all risk, an impossible task, but to manage it with a humility worthy of the power we hold. Our journey to cultivate other worlds must be guided by a cautious optimism, a commitment to learn as we grow, ensuring that the legacy we plant among the stars is one of wisdom and life, not unintended harm. The sheer complexity of cultivating another world defies any single perspective. We cannot engineer an ecosystem with the tools of biology alone, nor can we manage a global climate with only an engineer's blueprint. This grand endeavor demands a fusion of minds, a collaborative effort spanning every relevant discipline. Molecular biologists designing a new microbe must work hand in hand with planetary geologists who understand the mineral composition of the Martian soil that microbe will inhabit. Climate modelers need to predict how the gases released by trillions of these organisms will alter atmospheric pressure and global weather patterns over centuries. Ethicists must be at the table from the very beginning, helping to draft the principles that will guide our actions and ensure we proceed with wisdom. This is not a task for one nation or one specialty. It is a common project for all of humanity. We already have a powerful prototype for this kind of cooperation orbiting high above our heads. The International Space Station stands as a testament to what we can achieve when we choose to work together. Once fierce competitors, nations now share the same life support systems and conduct research in a laboratory built from modules crafted across the globe. This spirit of shared purpose is the exact model we must emulate on a far grander scale. The partnerships forged in the effort to become a multi-planetary species could have a profound ripple effect back on Earth. As we pool our intellectual resources and share the risks and triumphs of settling new worlds, we build bridges of understanding that transcend terrestrial conflicts and political divisions. This shared, aspirational goal unites us not as separate countries, but as a single crew on a planetary spacecraft, working toward a future where our civilization no longer has all its eggs in one basket. This collective journey reshapes our identity, reminding us that the most important border is the one between our fragile biosphere and the great cosmic void. Our journey began with a single, transformative idea that the future of space exploration will be grown, not just launched. We have traveled from the molecular machinery inside a bacterium to the scale of entire planets, seeing how these microscopic allies can become our construction crews, our life support, and our farmers. They are the quiet architects of a new reality, offering a path to sustainability that brute force engineering could never achieve alone. This biological approach is not about replacing technology, but about fusing it with the ancient, proven ingenuity of life itself. It redefines our relationship with the cosmos, shifting our role from explorers who pass through to creators who cultivate. We are learning to become gardeners of worlds, nurturing ecosystems into being with a careful and humble hand. The promise is a galaxy not of sterile outposts, but of living, breathing habitats, all made possible by the smallest life forms we know. As we stand on this threshold, the most critical tools we bring are wisdom and a profound sense of responsibility. The future we are building among the stars is indeed biological, a testament to life's incredible power to adapt and flourish. We would love to hear which of these microbial applications captures your imagination the most. Is it the idea of self-healing fungal homes, the bacterial miners unlocking asteroid wealth, or the cyanobacteria slowly painting a sky blue? Share your thoughts in the comments and subscribe to join us as we continue exploring the technologies shaping our tomorrow.